Now I'd like to talk a bit more about instantaneous velocity. In the previous video, it was more on the mathematical side. What do we mean when we limit the time duration to 0? Okay, so those were a bit more mathematical. So now I'm trying to get a bit more practical. So I'm going to talk about, if you talk about instantaneous velocity, how do you visually represent it in a diagram using vectors? Okay, we know that vectors get longer and longer, greater magnitude, pointing what direction signifies the direction of change of position, right? Let's study that a bit more holistically, okay? So instantaneous velocity, when we talk about velocity, there should be a magnitude and a direction because it's a vector quantity. So if we talk about magnitude of velocity, to determine the magnitude of velocity, we really need to know how fast the person is moving at that particular moment. Okay, let's say if I focus on specific time t over here, I have to know how fast the person is moving at time t in order to fill in the blank for the magnitude of the velocity at time t. Okay, so that means that the magnitude of velocity actually represents how fast the person is moving. Is not in moving, is moving. Okay, so we should expect that the magnitude of velocity is somehow related to speed, because we said just now speed is how fast the person is moving. Okay, so again later we'll see magnitude of velocity is represented by the length of the arrow that represents the velocity vector. Okay, next we talk about direction of velocity. Direction of velocity must be in the same direction as the direction of motion. This is what we mentioned quite in detail in the previous video, because it's a short window. You are unable to make complicated change in path to reach from the initial to final because it's such a short time. So if the path is like this, you should expect the change of position to be exactly the same as the path. So the direction of the velocity vector should be the same as the direction of the motion itself. So this is what we say, velocity is in the direction of change of position. Okay, so let's try to apply what we know here in this diagram over here. Let's try to label the vector arrow representing velocity at time 0, time 1, time 2, and time 3. Let's say for time 1, we want to put in the vector arrow to represent velocity. How do you put it? We know that this person is going to move in this towards the right. It's going to move in the positive x direction. So we should expect our arrow to be pointing to the right. Yes, that's the first thing. But if you remember the magnitude of v, we have to consider because that determines how long is my vector arrow. And as you remember in this example, I start with standing still first. I'm standing still, then when time starts, only I start to walk or run or sprint towards the right. So initially it should be at rest. So if at rest, the magnitude of v should be 0 because not moving at all. So we should expect no arrow at all at time 0. Okay, so the velocity vector is nothing at time 0. But for time 1, it'll be a bit interesting because you know that the motion, it'll be moving from the origin towards x equals to 4. The motion is towards the positive x direction. So we should expect the direction to be towards the positive x direction. But you know that after that, he or she is going to make a U-turn, and now it'll be traveling to the negative x direction or the left. So where should I be pointing? I should be pointing to the right or I should be pointing to the left. Now this is where we might get confused because direction of motion, there's two direction of motion. I come in from the left towards the right. I go away from the right towards the left. In that case, where's my direction? Well, no, you don't need to determine the direction. Why? Because the magnitude of velocity at this point is 0. At this point, when you're making a U-turn, you have to have a little stop. When you have a little stop, the magnitude of velocity is 0. Or how fast the person is moving? It's not moving at that particular moment. Or we can say the speed is 0. Okay, so in that case, we know that it's 0, so there should not be any arrow over here as well because it is at a stop before changing direction. Now we move on to T2. we know that t2, the direction of motion, it will be towards the left. So you know the arrow should be pointing towards the left, because direction of velocity, same direction as direction of motion. But how long is it? Well, in this case, you just know that it's moving, so you just write an arrow of this size. Okay, we don't really care about it. Let's keep it qualitative for now. And let's move on to T3. T3 is the last moment in this example. So T3 again, since this person is still in the motion of running, we expect that it will continue to move forward after T3. So let's put in the velocity vector. If we expect this person to be running faster than the initial T2 moment, okay, if it's running faster than T2, represented by this speed line over here, then we should expect a longer arrow vector that represents velocity, because that means it's traveling faster. Faster means greater magnitude of velocity. Greater magnitude of velocity, longer vector arrow that represents velocity. But today, if at T3, I'm not really sprinting, I'm not getting faster. Instead, I'm slowing down. I'm getting tired already. So if I'm getting tired, I should expect a lower speed, okay, a smaller value for speed. So the magnitude of the velocity actually gets smaller compared to the magnitude at time 2. So what does it mean? It means the vector arrow that represents velocity at time 3 should be shorter than the arrow vector that represents the velocity vector at time 2. Okay, so this is what I'm trying to say actually in this video. I'm just trying to say how should you visualize the velocity at different moment in a situation. Okay,